This video is a solution to free response question number 2 from the 2016 AP Physics 1 exam. My assumption in making this video is that you've got the question itself on a different screen or a printed out copy to stare at. This question was a 12-point, 25-minute question, and it is about an experiment that we need to design regarding a toy ball which is advertised to bounce perfectly elastically. We know that in perfectly elastic collisions, both energy and momentum are conserved. And so if we were to collide that ball with a hard surface like it's talked about in the problem, then we should expect that all the energy is conserved and all the momentum is conserved. The student makes a hypothesis that when the speed of the ball is low, when the collisions occur at low speeds, then those collisions will be perfectly elastic. But as the speed of the ball increases, we will deviate away from that perfectly elastic relationship. And part A asks us to design an experiment that tests that student's hypothesis. The ball has to bounce off of a hard surface, and we need to determine whether or not there's perfectly elastic collisions at low speeds and whether or not that relationship deviates at high speeds. Part A asks us to design an experiment to test this student's hypothesis, and part A1 specifically asks us to state what quantities we're going to measure. There are many different ways to come up with an experiment here, but there are a couple things that we need to make sure that we do in order to have an experiment that is reliable. And I think one of those things is our experiment needs to happen in the vertical direction. It's easiest to control what's happening to the ball if I just drop it. And so for that reason, my experiment in general is going to be, I'll drop a ball from a certain height, and we'll call that height h. So it's released from a height h above the ground. When it reaches the ground, it's going to be moving with a certain speed, v initial, and then after it rebounds off of the ground, it will be moving upwards, and I'll call that speed v final, just so we have a way of talking about it. One way that we could take care of this is we could measure just v initial and v final. If I know the speed of the ball right before the collision and I know the speed of the ball right after the collision, then I could tell you whether or not energy and momentum were conserved or not conserved just from those two measurements alone. Assuming that I know the mass of the ball, then I can calculate the momentum m times v, and I could calculate the kinetic energy 1/2 mv squared. An alternative way of doing the same sort of thing in maybe a different experiment is I could measure the drop height h, and I could measure the return height, which maybe I'll call h final. So maybe I'll call these h initial and h final. So maybe I drop the ball from a height, h initial, and then when the ball returns to its height again, maybe it goes up to a slightly different height, or maybe it goes up to the same height, but I could call that h final. Either way, I think we could determine whether or not the collisions were perfectly elastic or not. If we expect the collisions to be perfectly elastic, then in the first case, where I'm measuring the two speeds, those speeds should be the same. And in the second case, if I'm expecting the collisions to be perfectly elastic, we should expect the two heights to be the same. If the heights change, for example, if hf is less than hi, then we're losing some energy to the ground, which means that energy is not conserved. Lastly, before moving on here, I'm saying that I only need to measure the speeds or I only need to measure the heights. If I knew the masses, I could calculate the momentum or the kinetic energies, but really I don't even need to know the mass of the ball because I know that the initial momentum, the final momentum, the initial kinetic energy and the final kinetic energy all include the same mass of this same ball. And for that reason, I could really just compare the initial and final speeds, the initial and final heights to figure out whether or not these quantities were being conserved and whether or not the collisions were perfectly elastic. Part A2 asks us to further develop the experiment, part A2 says, what equipment would be used for the measurements and how would that equipment be used? Whenever a question like this is asked of you, I think the best way to do this is to just keep it simple. Don't have too many things. Don't list equipment that's unnecessary to the measurements that you're making. And so we'll try to keep this simple. For the first experiment where I just want to measure the initial and final speeds of the ball, what equipment would I need for that experiment? Well, one great tool that we have is a photogate. A photogate could allow us to really easily measure the speed of the ball right before and after it collides with the floor. We just need one photogate. On the way down, the ball blocks the photogate, and the photogate can measure the timing of that. And on the way up, the photogate could measure the speed again. As long as we tell the photogate what the size of the ball is, then we'll be okay. I think with the photogate alone, we would be able to make all the measurements needed for our first experiment that we came up with. A couple of things that we need to be careful of is we need to make sure that the photogate is not so low to the ground that we're messing up the measurements that we're getting. The photogate would need to be at least as high up as the diameter of the ball, so that way the photogate can come down, the ball can come down, pass through the photogate, hit the floor, and the photogate is not detecting it anymore before it bounces back up and blocks the photogate again. And so for that reason, it may become important for us to measure the diameter of the ball, because part of A2 really does say, and how would that equipment be used? So we would need to very specifically state that we need to have the photogate be as close to the floor as possible, but at least the diameter of the ball above the floor, so that way we get two separate measurements of the velocity that aren't affected by the collision with the floor. For the second experiment that we came up with, the equipment that I need is a little bit different. The equipment I need here, in order to measure the initial height and final height, is for sure at least a meter stick. But then, I think if we want to reliably measure the initial and final heights, especially the final height, we will also need a video camera. And so in my response, I'm going to say I need a meter stick so that way I can measure those initial and final heights. But in order to do that reliably, I'm going to also need a video camera, because that video camera could be analyzed after the fact. I don't have to try to read the heights of the ball as it's happening live in the experiment. All right, so at this point we have an idea. We're either going to measure the speeds before and after or the heights before and after the collision. We're going to use either a photogate to measure those speeds or a meter stick and a video camera to get the heights. And now in part A3, we need to pull all this together and describe the procedure that could be used to test that student's hypothesis. So now part 3. And I'm not going to write the whole thing out, but I am going to talk about a few things that we should probably include in our description of the experiment. The first thing that we need to talk about is, what are we going to do? Right? So there I'm probably restating that the photogate needs to be in place, and we need to drop the ball from a height such that the photogate can read the initial and final speeds. In the second case, I need to state that I'm going to drop the ball along the length of the meter stick, so that way I can record the initial and final heights using my video camera. And obviously you need to make sure that the meter stick is high enough such that it's there so I can see the release position of the ball and the return height of the ball on that meter stick, which if you're trying to go to pretty high heights, then maybe you need a couple of meter sticks. The second thing that I want to make sure that I do is I need to address this idea of low speeds versus high speeds. And so how do I generate low speeds and how do I generate high speeds? Well, this is you need to understand a little bit about kinematics or a little bit about energy in order to do this. If I want the ball to collide while it has a high speed, then I need to release the ball from a greater height. And if I want the ball to collide at a low speed, then I just need to release it from a lower height. Because we know the less distance the ball has to hit the ground, the less time it has to accelerate, or the less gravitational potential energy it has to convert into kinetic energy. And so somewhere in part A3, you need to describe how you're going to do that. And inherently, what we're saying here is that we need to do multiple trials. Multiple trials. And really, in any experiment that you describe, it's always a very good idea to make sure that you indicate that we need to do this several times. Not only because it adds some reliability and reduces some of the uncertainty that we'll have in our final measurements, but here it's a requirement because we need to test a full range of speeds. We need to make sure that we have data that goes with low speeds and data that goes with high speeds, because ultimately the student's hypothesis was a claim about what happens between the ball at low speeds and high speeds. I think that's enough for part A. Just realize that, if you were answering this as a free response question on an exam, then you need to make sure that, the bulleted lists that I'm showing here is not exactly what needs to be on your answer sheet, right? Especially for part A3, where it asks you to describe the procedure such that there's enough detail for another student to replicate the experiment. You need to write clearly and in a way that can be understood, and you need to make sure that you're not including any extra information that's unnecessary. Now moving on to part B, which says, describe how you would represent the data in a graph or a table. Explain how that representation can be used to determine whether the data are consistent with the student's hypothesis. I think we have the free choice here to make a graph or just use the data to validate the student's claim or refute the student's claim. I think that maybe for the first experiment we'll do a data table, and then for the second experiment we'll do a graph. So in the first experiment I have a bunch of final speeds and I have a bunch of initial speeds. And I think that if we did this experiment, then we would have several trials of data that would show here's the final speed and here's the initial speed. One calculation that we could make that could prove that could show whether or not the collisions were perfectly elastic is we could find the difference in the squares of the speeds. So if we found v final squared minus v initial squared, that would tell us whether or not the collision was perfectly elastic or not. The reason being is kinetic energy depends on the square of the speeds. So the change in kinetic energy is proportional to vf squared minus v initial squared. And so if we took all of our measurements of final velocities and initial velocities and did this, then we should expect that at low speeds, so maybe here in my data table I have low speeds, then I should find, if the student is correct, that in that region of the data table I would find that this is approximately 0 for all those trials. And why is that? Is because if the collision is perfectly elastic for low speeds, then the difference in the kinetic energy should be approximately 0. And then as the speeds increase, which essentially means I'm dropping it from a greater height, and we get to the high speeds, if the student is correct, then we would find that we would be getting further and further away from 0, and actually the difference in the squares of the velocities would start to become negative. The reason why it would become negative is because if the collisions are not perfectly elastic, the initial velocities would be greater than the final velocities, which means that the difference in the squares of those velocities would be negative. And so, we can't say for sure because we don't have the ball that's being described in this experiment, but if the student is correct, this is what we would see in the data table. And then, of course, if we found a different relationship, or if it was approximately 0 within the uncertainty of these measurements for the full range of speeds, or if it was negative for the full range of speeds, then we would be able to say that the student's claim is not quite correct. For the second experiment, where we measured the heights, I think it's best to make a graph of the final height versus the initial height. We could do something like we did for the first experiment with the data table, but I just want to have an example of a graph and a data table. Clearly, if we subtracted the heights and the initial height was greater, then we would get a negative number, and then we would be able to describe what that means in terms of the energy conservation. But if I make a graph, if the final heights are equal to the initial heights, which means I drop the ball from a meter, it comes back up to a meter. I drop the ball from 0.8 meters, it comes back up to 0.8 meters. If that's the case, then for every initial height, we should get an equal final height, and we would have a line that looks like this. So to be clear, if we did this experiment and our data falls along this dotted line, we have several trials that occur at low heights, which correspond to low speeds, and then we have several trials which occur at big heights, which correspond to big speeds. If they all fall along that line, then that does not support the student's claim, because the student's claim is that those heights would be the same at low speed collisions, so at low heights, but then when we increase the speed by increasing the height, then it should vary from that line. And how should it vary? It should vary such that as we get up to bigger heights, the initial height is greater than the final height. So we should expect that if the student's claim is true, that it would follow this linear trend at low speeds, but then as we get up to higher speeds, it should deviate from that line. It shouldn't be linear anymore. The initial height is not going to be met by an equal final height, and so it should taper off like this. And then we could probably justify that in this graph there's some region, that we could call low speed collisions and some region that we could call high speed. Maybe these are the low speed and these are the high speed. Low and high are relative words, but we could make this graph and show, hey look, the heights are equal at low speeds, but at high speeds they deviate from one another, and this seems to validate the student's claim. Of course, knowing what we know about conservation of energy, that blue line could never go north of the white line, right? A line that could never exist is this red line, because unless there's an external force that is acting on the ball, then the final height cannot be bigger than the initial height. For most real objects, we're going to get something that looks like the blue line, but if the ball is advertised, as it says in the problem statement, that it's supposed to bounce perfectly elastically, then really it should be following the white line. I think this is enough for part B. We just needed to make sure that we say what we're going to do, either the table or the graph, what we're going to do in that table or in that graph, and then how that representation of the data can be used to show whether the data are consistent with the student's hypothesis. So some of the writing I'm saying to you, but that would need to be written in your explanation. The last part, C, says, a student carries out the experiment and analysis described in parts A and B, and those are the things that we talked about. So, at this point you've picked one of these experiments and have been describing that all the way through, not both. So after carrying that out, the student immediately concludes that something went wrong in the experiment because the graph or table shows behavior that is elastic for low-speed collisions, but appears to violate a basic physics principle for high-speed collisions. C1 asks us to do the following. It says, give an example of a graph or table that indicates nearly elastic behavior for low-speed collisions, but appears to violate a basic physics principle for high-speed collisions. So something that would indicate nearly elastic behavior for low-speed collisions is, kind of things that I've already described. So if you're doing the experiment on the left, then you need to say something about VF squared minus VI squared being approximately 0 for low speeds. This demonstrates nearly elastic behavior for low-speed collisions. Now, what in my graph would demonstrate something that violates a basic physics principle for high-speed collisions? Something that would violate a basic physics principle would be VF squared minus VI squared is equal to a positive number for high speeds. Why is that violating a basic physics principle? Because if VF squared minus VI squared is a positive number for high speeds, then that means the final velocity was greater than the initial velocity. And I know that if I drop an object, at best, it's going to come up with, a speed that's almost equal to, but a little bit less than the initial speed that I dropped it with. And for that reason, the difference in those quantities cannot be positive. That is a violation of the conservation of energy, because I have more energy than when I dropped it. Continuing on to our experiment that we've described on the right, where we're measuring the heights, I've essentially already gone through this. The graph would illustrate nearly elastic behavior for low-speed collisions if the graph of HF versus HI is linear for low speeds. And we could use a graph or a data table to say that at high speeds, if HF is greater than HI, at high speeds, should go back, at high speeds, then we've also violated the law of conservation of energy. In which case, we should expect that maybe there was a mistake that was performed in collecting the data, or a mistake that was made in making the graph, because we could never obtain final heights that were greater than the initial heights. And with this, the last part of the question is part C2, which asks us to state one physics principle that appears to be violated in the graph or table. Although several physics principles might appear to be violated, we only need to identify one. Here, I think it's easiest to just talk about the law of conservation of energy. And the reason is because quite clearly we know that if energy is conserved, then the final speed can't be greater than the initial speed, and the final height can't be greater than the initial height. One thing that I think I should point out is in part B, where we made the table and the graph, really they were not asking us to actually make that table or graph. They were just asking us to describe how we could represent the data in a table or a graph. So just kind of describing the setup. But then in part C1, it actually said to give an example of that table or graph that would indicate the behavior that they were asking for. So, really I kind of wrote this a little bit backwards, but you could, as long as you had the question in front of you and you were reading the directions carefully, then I think you would be able to see that pretty clearly. The big thing here is make sure that part C2 ties into part C1, and make sure that part B ties into your experiments in part A. So that way it all is tied together. You want to make sure that at the beginning of these design and experiment problems that you have a vision for the experiment, you know what you're going to do, and that way you can carry that throughout all the parts of the question.